Okay, let's get started. My name is Kathy Erickson, and I'm the moderator for this session. I will be introducing our speaker in a minute, but first a note that you've probably heard before today. If you have questions, you won't be able to break in with your speaker, so we would like the questions to go through the chat button at the bottom of your screen. And Scott said that he will take questions as he goes along, and I'll help monitor so that I'll let him know if there's one up there that he hasn't noticed. So our topic coming up is identifying invasive Japanese knotweed using drone imagery. The speaker is Galetka from Bayfield County Land Records. Scott is currently the Land Records Administrator and Land Information Officer for Bayfield County. He manages the survey, real property listing, geographical information systems, UAV/UAS/drone, and land sales functions. Scott will talk about how Bayfield County used the drone to detect knotweed populations, different camera types, how the imagery is stored and accessed, and the potential for drone use, detecting a few other invasive plant species. So go ahead, Scott.
Thank you. My name's Scott Galetka. I've been working for Bayfield County, probably 12 years or so. And our recent purchase of drones and some different cameras throughout the past 3 years kind of created a very unique program for us here. We just don't focus on invasive species and conservation issues. We also work with the Sheriff's Department and zoning departments and forestry. The Forestry Department also has some drones there that they use for their own purposes of finding diseased trees and beaver dams and such. But our drone program basically started like 3 years ago. So, and we try to help all of the departments in that. So I think go to the next slide. So a little bit of demographics about our county. We have about 1,500 square miles of land, second largest county in the state. It takes quite a bit of time to get certain places. Luckily, I live in the center of the county, so if I'm going to do a drone flight, I can leave from my house, and it cuts down the travel time by quite a bit. We have 4 islands: Eagle, Sand, York, and Raspberry, and almost 100 linear miles of Lake Superior shoreline. We have also 51% or slightly above that in public ownership. The majority of that is federal forest, and then county lands, and then after that it would be state. We also have a lot of lands that are in private ownership that are open to the public in managed forest programs. The population in the county is about 15,000 people, and it typically triples during the year, during the summer, I'm sorry. And this year is going to be fairly unique with COVID. I was up in Bayfield the other day, and it seems like quite a bit less people. Everybody is, I think, staying closer to home. Next slide. So kind of jumping right into it here, Japanese knotweed is a pretty invasive species. It's originally from East Asia. It bears some resemblance to bamboo. It has a broad leaf. Some of those leaves can be about 12 inches in size. So it makes it really easy to see with aerial imagery. And during the late summer, it produces some white flowers also that make it unique to see from aerial imagery. It grows aggressively and it can spread along water, rivers, streams, or through movement of soil on logging equipment, dump trucks, and all that kind of stuff. Next slide. It has a very invasive root system. It can get into foundations, bridges, roads, so it's pretty destructive. And it grows tall, and the leaves are large and loves the sun, so it chokes out everything around it once it starts growing in a certain area. It spreads through rhizomes and shoots that can reach out 23 feet from the original plant. So it spreads pretty prolific. So all the roots need to be killed to eradicate it. It's very difficult to control, as applications and herbicides or cutting require multiple years to be effective. And I'll have some slides in a little bit that kind of show that. Next slide. So one of the ways that we thought about trying to quantify and manage our treatments is using aerial imagery. There's basically three sources of information that we can get from aerials: is satellite imagery, aerial photography, and we also have drone imagery that we can produce on our own. The satellite imagery, there's 2 passes over Wisconsin a day, and they happen around noon. And some of the things that happen with that is there's a lot of cloud cover that may cover the areas, and the resolution isn't the best. So you have big patches of knotweed. You can probably see that growing in that aerial imagery. But if you have some outliers, single plants, you probably wouldn't be able to see that. Our next option was looking at area photography that the county produces. We typically fly the county every 5 to 6 years, and that's not really a good way to manage our effectiveness on our treatments. And we usually produce those flights during the spring before leaf out. So a lot of that, it doesn't really show up in our aerial imagery unless we have a really late flight. The beauty about drone imagery is it produces a very high resolution photo. You can get 0.5 to 1 inch resolution aerial imagery, and you can choose when you want to fly, depending if the weather conditions are okay. It can be sunny, you can fly under the clouds. Your biggest limitation is probably the wind, and as long as it's not raining. And you get to pick the time of year that you want to fly. If you know that the Japanese knotweed, or let's say another invasive species like purple loosestrife is blooming, you can hit that target date or that time of year when it really pops in that aerial photography. The other thing that you can do with drones versus going on foot or with a boat is you can get in certain areas that you may not be able to get to on foot. The only thing that you really need is a licensed pilot and the equipment to do that. All right, next slide. So these are the images of our equipment. The largest cost, and probably the maintenance of it, is probably your batteries. Some of these batteries for the unit that we have, M200, is about $400 a piece, and it takes 2 of them, and you get about 30 minutes per flight out of those. And because that we don't just use it for invasive species, we also use it for search and rescue, different wildlife projects. We're always, trying to back buy some of those batteries, and your batteries are probably going to cost more than your unit to fly with. Ooh, I got a couple questions.
Yes, there's a question here. How can you see it so well when almost everything else is green?
That's a good question. Japanese knotweed, and I'll kind of get into this a little bit later, but it really pops up because it's more of a lime green color than the surrounding areas. And in some future slides, what I'll show is it does get confused with some other vegetation, but we found a way to get around that. I'll cover that in a little bit.
Okay, thanks.
The Ultim, so the Matrice 200 is one of our workhorses. We also have a multispectral camera. That's that red camera with a bunch of different lenses on it. It has 6 bands, and it separates all the color. So typically when you look at an image, you see 356 colors. This separates them out into individual black and white colors of red, green, red edge, near infrared, and there is also a thermal sensor on it also. So we have the capability of combining different bands together, which make it very unique. We haven't gotten into it that much, but we have the capability, and we'll probably do more of that this summer. We also have an X4S camera. It's probably one of the best cameras out there that they had for our current system, and it was very reasonable cost. The Ultim sensor was about $12,000, and that has a lot of features to that, and the county's made a lot of investment. The X4S camera, it was about $500, and the drone itself was about $4,000. Since we brought all these uses together, that justified that purchase of that system and program, and decided to put it in the land records department because a lot of it has to do with aerial imagery and mapping. So we have the capability to share that imagery online fairly easy and relatively quickly. So one of the things that we can do is we can fly an area, get that process to make a orthomosaic, basically create a map and publish that map online through our interactive map within a couple days. So, all right, thank you. Next slide. So this is our site that I'm going to talk about. It's a C&W gravel pit. This was flown with the Ultim multispectral camera, and it's about 65 acres. With the drone, it took about an hour to fly this area. And the conservation department said that it'd probably take them a couple days on foot, depending on the accessibility to search for Japanese knotweed in this area here. So it cuts down quite a bit of time looking for this weed. The box on the right-hand side is an area that we'll focus on throughout the presentation here. And the lower left image is a blow-up of that box. The circles are Japanese knotweed. That small circle on the top left is one kind of bush of it there. And you can see how that green stands out from the other green around it. And then the bigger circle, you can kind of see that happening also. There's that lime green, lighter green, and then there's the darker greens within it that are trees popping out of that. All right, yep. Next slide. So our first basically kick at the CAD was to do a supervised classification. And the definition of that is the task of extracting information classes from a multi-band raster image. So basically what we're doing is telling the pixels, each little square, what it is, or the groups of squares, or what that is. So the supervised classification takes user-defined training data and assigns the pixels in that image into class types based on the spectral values. So basically, we make polygons of, let's say, a tree. It takes all those colors and says, oh, this is a tree. And this color range is what we're looking through in the rest of the photo. And it does it by pixel. So some of the things that we need are the spatial analyst license. And we use ARC products when we do our mapping. And then later on, I'll talk about an object-based analysis, and that is we need image analysis for that. Next slide. So part of the first steps of doing the analysis is using ARC Pro, we used ARC Pro in this process. You can use ArcMap. ARC Pro has a few more wizards to make the process go a little bit faster. It also creates some temporary files, so we can rework the data after we run it once. We can run the process again. And I'll run through that a little bit down the line here. Next slide. So this is a pixel-based classification. We use the default schema. Basically, the schema is a list of objects that we want to find in that image, such as roads, forested areas, and you can break that down into shrubs versus, coniferous and deciduous, and you can get that detail. If you already have some image or some schema already defined, let's say this is a project area that you want to fly multiple times, what you can do is use that same training polygons for your training for the next sessions. One of the things that you want to do if you're doing multiple flights of the same area, basically you're doing the multiple flights to monitor your treatments throughout time, you want to set some sort of GPS control. And what I mean by that is creating a control point with a V or an X painted on the ground, and an exact location for that. You should be able to use a resource grade for that. And what that does is when you're doing those multiple flights, you have separate images, data sets, and it aligns those pixels up quite a bit better, so you don't get any shift in those multiple flights. All right, next slide. So this is part of the NLCD 2011 classes. These are the defaults, and Knotweed doesn't come in that default. So one of the things that we did is we added Japanese knotweed, and the forested areas, we don't really care if it's deciduous, mixed, or evergreen. So we deleted those classes and we just called it forest. If you add more classes, your classification of the imagery gets a lot better. So next slide. So these are our final classes for our pixel wizard. So we used water, developed areas, and grouped roads and roofs and cars in there. Barren areas, which would be dirt and gravel. And our roads, I think, was included in that also. Forested, we grouped all those tree types together. Added Japanese knotweed. Background color. Sometimes you get this black area, which is a no data part of the aerial imagery. It's when you're processing the imagery, it wants to create a square object, and you're not always flying in exact square areas. So the background is all other data that's no good. Shadows. So shadows can be really tricky. One of the best things that you can do is probably fly underneath the clouds so you don't have those shadows, but that also offers some challenges also. When you're flying in a lower light, you have to fly much slower. So it allows more light to get into that camera and you get a crisper image. So typically I've had really good luck in flying under thin cloud cover. Next slide. So these are some training polygons in the image to the right. In the image, there's a square polygon. In the road, it's kind of a light yellow color. That all those pixels will be classified as roads. So it'll search our entire photo and say, yep, these are roads. And then there is those red areas. Those are polygons that contain 100% Japanese knotweed. And then the green areas are the higher tree cover. So we have, I think there's like 9 or 10 different classes. So for each class, you need a minimum of at least 5 polygons throughout your entire image that you're trying to find determine what classes are in there. And you want to equally space those out throughout your whole image. Next slide. So this is our site again. We have polygons spaced out through our entire image. Yep. You got the blue ones for water. Go clockwise down below. You have the green area there. I don't know what that is. It looks like grassy areas, which would be lawn. Then in the middle, we have barren areas, more gravel, zero vegetation. And we should have some of those would be rooftops. And what else we got? And then in those red areas would be Japanese knotweed. those are sites that we know that we looked at the aerial photography and said, yes, we know for a fact this is Japanese knotweed. And you can look on the classes there. We said there's roughly nine samples of the background color, and it's in black there, but down below on the bottom of the image, right there, that's our no data. So we said that's not part of our project at all. And we got, 5 water spots and up to 23 different samples of the other features. All right, let's let her run and hit the next slide. This is what we get. So some of the first few attempts aren't always the best. So what you want to do is go back in and create some more polygons. So we have a lot of, it kind of looks like a speckled painting here, because it's looking at each individual pixel. The red areas in this picture says there's knotweed there. We know that all those areas are probably not knotweed, and what we want to do is go in and filter some of that out of there. It did pretty good on the water areas, the top right and toward the middle. That's classified as water. All that green area is, it's vegetated forest. Did pretty good on the lawns, that lime green. But we really want to pick out that Japanese knotweed and really zero in on that. All right, so after we created some additional polygons, I think we went through, next slide. There you go. We found out that it was confusing sumac and Japanese knotweed. So we wanted to do a better job at defining those pixels or those polygons in there. So on the ground, I knew, this is sumac and the differences between the two. So we reran the analysis. So all that red on the left-hand side, that was majority was sumac. So, all right, next. So that was our initial result. We got a lot less red. It's starting to make a little bit more sense, but we still have that splattered effect to our results. So what we wanted to do then is clean that up a little bit more. Next slide. So we ran a clean on the image to give it a smoother look. We ran a majority filter and a boundary clean. Basically, buttons on the computer. So we hit those few things to clean it up a little bit better. The next thing that we did is we took that raster imagery and created polygons out of it to create vectors. From the vectors, it makes it easier for us and less intensive on our computer to run some comparisons. So we looked at the digital terrain model and digital surface model with our LiDAR. And that's our LiDAR is a digital elevation model of a bunch of X, Y, and Z points of all the vegetation. And we were able to, using LiDAR and these other two products, to say anything over 10 feet, get rid of, because we know Japanese knotweed doesn't get much taller than that. The other thing is we also eliminated anything that was 0.2 square meters in size. So any little specks in there, we said get rid of those two, clean those up. Those are probably just anomalies in the database. All right, next slide. So this is what we got. It looks really good. So on the left-hand side, we have that same area, and on the right-hand side, you can kind of see it really picked it out fairly well. But you see some holes in there. It didn't really group it up. So when you try to run some analysis of how many acres of this wheat do you have, all those little holes create problems, and it's going to say you got less acreage than what you really have. So what we wanted to do is get a little bit better with that. And next slide. So the next best thing is an object-based situation. It doesn't just look at the pixels. It looks at the shape of the objects and the context where it's located to other things. It also looks at the texture of the training data that you create, along with those pixel returns. So you're kind of bordering on some artificial intelligence stuff, but you're telling it what to look for. And it's a more tailored approach to the classification. Along with that, we needed to do a license upgrade to Image Analyst in ArcGIS. Next slide. So if any of you have used pastel colors, that's kind of what this image on the right-hand side looks like to me. So basically, what we do is we run it through a wizard, and it segments all those colors and textures, and it uses all that information. And then there's three main parameters that it uses. It's the spectral detail, the spatial detail, and the segment pixel detail. The first two seem like it does the most to be able to get that contrast of where that those boundaries of each feature are. And you can really get it super detailed, but then you're spending a lot more time grouping and saying, this block of colors is this, this is this. So there's a happy medium of too much detail and not enough detail. You want to pick a level that is right for your project. And it depends on the camera you use, your conditions that you're flying in. All right, next slide. So after you have your pastel painting, basically, and it creates these raster polygons. So you want to classify those. And on the image on the right-hand side, you can see the red is a polygon of Japanese knotweed. And that was the first run-through of our process. Let's see, is there anything else I want to say about that? I think that's good. You get that, it's not as speckled as the pixel-based image analysis. Next slide. So this is our initial result of our object-based classification. It looks very similar to our final result over pixel-based. So with less steps of the object-based, it seemed like we were headed on the right track. But there's still a lot of red out there. We felt that we're getting some false positives on it. So we ran it through the same process that we did before with the pixel-based. We are deleting all the information that we think is bad. Next slide. Yeah, okay, this is more the close-up of the clean up. And you can see it looks pretty good on the right-hand side when you see a close-up of that. That Japanese knotweed is pretty covered by that red area. All right, next slide. So this is where we ran through that cleanup again, basically extracting those raster polygons into vector polygons, overlaying it with our elevation data, getting rid of everything that was too tall, and again, anything that those polygons that were too small, we also deleted. Next slide. So these are our two results, final results, side by side. On the left-hand side, in yellow, you have the pixel-based. So it still has that scattered look to it, and kind of that, I call it spray almost, but it's giving a lot of false positives still. And then on the right-hand side, we have the object-based. And you can see those areas of red that give it more blocky look to it, more like how knotweed actually grows. Once it hits an area, it kind of spreads out into big areas. All right, let's hit the next slide. So what we're doing here is comparing the two different results. The result of the object base, basically the pastel colors, is in red. And that's the result of the knotweed for the object base. And the pixel based is in yellow. And the yellow kind of has that speckled look to it. And that is getting us not very good, not very accurate acreages on a invasive species. On the image on the right, we blow it right up and we zoom into the image. The outline in red, it follows that bush that we were talking about early, pretty much right on the money there. And the pixel based has a lot of holes in it. So that's going to skew our acreages off on that, on our amounts of Japanese knotweed. All right, next slide. All right, future improvements that we're looking at is utilizing different bands of the Ultim camera. One of the nice things I had is I had a really good employee last year. She had a master's degree in remote sensing, and she went off to do some bigger and better things, but we kind of really collaborated pretty good on a lot of stuff, and we were talking about using that multispectral camera more, and she had a lot of interest in using the camera and raster imagery and experience. So now that is kind of up to me and kind of teaching our replacement on that. So the other thing is flying when there's no shadows. That eliminates one problem from our camera or imagery. You know, you don't want to be flying in a super sunny day, and then all of a sudden clouds come through and roll in, and then your imagery has this different brightnesses to it, and that causes some images. So a homogeneous map is something that you want to shoot for. Also, the other thing is shooting the imagery at different times of the year. That way, if you know when it's blooming, with that really looks good and pops out in the imagery. And if you're doing multiple years or multiple times during the year, you can compare each individual image, so you can see what the best time of year is to fly on that. One of my wish list things is being able to look at those individual images. So what we do is we fly. When we're flying and creating these big areas and stitching all those photos together, we have about 300 to 1,000 different images. Is be able to analyze each individual image for that, because towards the edges of the image, you can kind of see the sides or underneath some canopy. And that would be nice to utilize some of that individual imagery. There's a product out there, it's called Locate, and it is typically for search and rescue, finding certain people lost in the woods, or if you know the color of the clothing that the person is wearing, you can do these flights, upload the imagery, and it goes through roughly 1,000 images in an hour. You can cover probably 500 acres in that area, and search for that color in each individual image. We want to do the same thing for Japanese knotweed or purple loosestrife or some other kind of invasive species. As long as we know, let's say we go out in the field and capture that color range, and then we can do that with each individual image versus merging all those images together, and some of that canopy covers the low-lying information. So next slide, and I think that's it. Yep.
Thank you, Scott. I have one more question here.
Mm-hmm.
Are there so many, or why are there so many wild knotweed patches in Bayfield County? Secondly, when you find them, how do you treat them?
So why are there? This particular site, I can't remember what the history is of it. A lot of people would buy Japanese knotweed at the, it's a nice shade bush, you buy it at a greenhouse or whatever, and maybe they plant it in the backyard and it just gets away.
Do you have more than other northern counties?
I don't know. This spot here is bad.
Yeah.
That's why we kind of used that that was our first go at it. How do you get rid of it? What they do is they go in and cut it and put herbicide on it and basically keep treating it like that.
Is it similar to cutting buckthorn?
Yeah, buckthorn's bad. I have that near my house. Yeah, it's pretty. Yeah, I would say. Yep. Buckthorn is a little more spiny, but yeah. Yep, I would agree. It's nasty stuff. Want to get rid of it before it takes off.
I have one more
Mm-hmm.
here from Andy Teal to everyone. Not sure how it arrived up at CW Trucking, but a bunch of sites have sheared it off and planted it on purpose.
Mm-hmm.
Bayfield County does have a pretty high number of patches compared to other northern counties.
Thank you, Andy.
Okay, very good. And thank you very much, Scott, for presenting to us.
Mm-hmm.
And to all the participants for joining us today. Remember that all the sessions of this conference are being recorded, and you will receive an email a follow-up survey and giving you access to look at the recorded versions of these sessions. Thank you, Scott. And everyone.
All right, thank you. Thank you for having me.